record. And then let's see if I can switch to something so I can write on a piece of paper. And then I need to pin this. And there we go. Again, I've almost exceeded my knowledge of what to do with technology. Okay, so let me try to write. And so I'm not quite sure what the title is, but I'll use this: Underapproximation by Egyptian Fractions. And I spoke about this sometime last year, but in the interim, I proved some things, and I want to say what they are. There is a paper on this, a preprint that I posted on Archive yesterday. So so no matter how sloppy I am in my presentation, you can find things that are legible and correct on Archive. So this starts with a classical result of Sylvester. So let me just start. So what's an Egyptian fraction? An Egyptian fraction is a unit fraction. That is something of the form 1 over x, where x is a positive integer. And it was Fibonacci, again, never the first, who know, and I have no idea who the first one would be, but it was Fibonacci who showed or wrote down a greedy algorithm to write any rational number as a sum of Egyptian fractions. So there is a greedy algorithm which you find in Fibonacci's book to write any fraction p over q as a sum of Egyptian fractions for all p over q greater than 0 and no greater than 1. And you write the fractions in increasing order. And the smallest is at least 2. And the greedy algorithm is simply, at every step, choose the largest Egyptian fraction, which means the Egyptian fraction with the smallest denominator that's less than or equal to what you've already calculated. And
should they be strictly increasing, or does that not matter?
They turn out to be strictly increasing, but this is all I want.
Oh, you don't assume it. Okay.
No, you don't assume it. I mean, just the greedy algorithm makes it strictly increasing. And there's a simple argument to show that it converges in a finite number of steps to the right answer. But so there's something slightly different from writing a rational number as a sum of Egyptian fractions, and that is the following. So let's say that you say summation 1 over xi, I goes from 1 up to n, under approximates some number theta. My thetas are always in this interval from 0 to 1. If summation 1 over xi is less than theta. So, and the classical result, which is the origin of all of these discussions, is Sylvester's observation that if you take a sequence Well, let me do it on a separate piece of paper. So this is Sylvester's sequence. S sub I. I goes from 1 to infinity. It's defined by S1 equals 2. And Si plus 1 is the product of all the S's from 1 up to, let's say Sj plus 1, is the product. J goes from 1 up to, I goes from 1 up to J, S sub I plus 1. So you get that S1 is 2, S2 is 2 plus 1, which is 3, S3 is 2 times 3 plus 1, which is 7, S4 is 2 times 3 times 7 plus 1, which is 43, S5, I mean, you can, it's not hard to do the calculation. S8, for example, I don't know if you can do it in your head. It's 113, 42371, 305542, 184436, 1000443. So, I mean, in old school number theory, you believe every now and then you should see a number. Number only means positive integer. And there we have a beautiful number, right? So that's the 8th number in Sylvester's sequence. And Sylvester proved, this is about 1880 or so, that the sequence S sub I equals 1 to infinity, is the, that's called the infinite greedy under approximation sequence for theta equals 1. So what does that mean? That means if you're trying to construct a sequence of rational numbers that under approximates some theta, at every point you pick the largest fraction that you can. So S1 is the largest Egyptian fraction, less than 1, which is a half. So you get S1 is equal to 2. S2 has to be the largest fraction, the smallest integer. So if you look at 1 minus S1, which is a half, you want the largest fraction, 1 over S2, less than 1 minus S1. So what's the largest fraction less than a half? It's a third. So S2 is equal to 3. And then you say, okay, what's 1 minus 1/2 minus a third? That's a sixth. The largest fraction less than a sixth is a seventh. So S3 is 7 and so forth. And Sylvester checked, and once you have the idea, it's not hard to check, that let's call it the greedy under approximation algorithm. So in the greedy under approximation algorithm for Egyptian fractions, at every step you choose the largest fraction, which you can add to the Egyptian fractions you've already calculated, and you still have an under approximation for your theta. I mean, if you're applying this to an irrational number, it's just the greedy algorithm, because you're never going to get equality. At any finite step, you only have a rational number. But this is Sylvester's theorem. And not too much later, in around the 1920s or so, there was a famous American mathematician, G.A. Miller, who studied group theory. And he was looking at conjugacy classes in groups, and in what is really a natural way, was led to the conjecture that for every n, the n-term sequence of the first n Sylvester numbers gives the best Egyptian under approximation of 1. So what this means is the following. So if you have a sequence of integers, the rational number it generates is just summation 1 over SI. I goes from 1 up to n. So when we talk about a sequence of Egyptian fractions, you can just look at the sequence of the denominators. So if you have an n term, so this is the sequence of Sylvester numbers. So it gives this under approximation of 1. And Miller's conjecture was that it's the best Egyptian under approximation in the following sense. If you have some other sequence of integers, so if xi, I goes from 1 to n, is any sequence of integers, which you can write in increasing order, which is at least as good an under approximation to 1 as you get from the Sylvester sequence, then SI equals XI for all I. So this says that Sylvester sequence gives the best n-term under approximation to 1, and in fact, the unique best term. I mean, in principle, you might have for some n, another sum of n Egyptian fractions equal to this sum of the Egyptian fractions that come from the Sylvester sequence. But Miller's conjecture was that that's not possible. And independently, so this was 1919, for anyone who's keeping score. And a couple of years later, these were by a guy named Kellogg. Kellogg was at Harvard, this was in 1921. He had a following very interesting paper in the monthly. It was called On a Diophantine Problem. And he writes, a few years ago, I made the statement that this is true. And I just tried to write down the proof, and I realized I couldn't prove it, but I still believe it's true. And so this is sort of my conjecture. He didn't know about Miller. But it seems like around the same time, these two guys, for different reasons, independently made this conjecture. And not too long afterwards, this was proved by a guy named Curtis in the US, and also by a Japanese mathematician, Takenouchi. So the classical result is that Sylvester sequence is the sequence you get by applying the greedy algorithm to under approximate the number 1. And this is, in fact, for every n, the unique best under approximation. Okay. So it would be natural to ask, for example, or to wonder whether this is always the case, whether for every number theta, if you take the sequence you get by applying the greedy algorithm, you get a finite sequence which is the best and maybe the unique best under approximation to your number. And that turns out not to be the case. And there are a couple of simple examples of that. Let me find one or two. Yeah. So let's take 1/3, which they teach you is less than a half. Okay? Which means if you take any number theta, which is greater than a third and less than or equal to a half, and you apply the greedy algorithm, the Egyptian fraction you get will be 1/3. 1/3 is the largest Egyptian fraction less than theta if theta is less than or equal to a half. But suppose, let's say, okay, that's good. So 1/3, of course, is less than a third. Let me guess a number. I'll try 1/17. Now, a third plus 1/17 is less than a third plus 1/16. All right? I think everyone will, I hope, grant me that. And a third plus a 16, that's less than a half, right? So if I take any number theta, which is greater than a third plus a 17th, and less than or equal to a third plus a 16th, and I apply the greedy algorithm, in the first step, I'll get a third. And in the second step, right, what does this say? This says that theta minus a third is less than a 16th and greater than 1/17. So the first two steps in the greedy underapproximation algorithm for any theta in this interval, right? What is this number? So this is for any theta greater than 20/51 and less than or equal to 19/48. For any theta in this interval, the greedy algorithm gives the sequence 317. But suppose I make some lucky guesses and I say, let's look at a fourth plus a seventh. Now, I'm assuming everyone here has made it through elementary school and can do fractions. Now, those of us who teach at CUNY realize this is not always the case. But 1/4 plus a seventh is, what is it? 11/28. That is greater than 20/51 and less than 19/48. So what that says is, if you take any theta, which is greater than 11/28 and less than or equal to 19/48, for any theta in this range, the greedy algorithm gives 1/3 plus 1/17. But that's strictly less than 1/4 plus 1/7. So this greedy algorithm does not give the best two-term underapproximation to all theta in this interval. All right. So here we have some big set of numbers, and if you only like fractions, there still are infinitely many fractions in this set. Infinitely many numbers for which the greedy algorithm, even with just two terms, fails to give the best underapproximation. All right. So this suggests many questions. Here are some of them. First, well, of course you can say, why not, right? What is wrong with the universe that this obvious greedy algorithm isn't always optimal? You know, I don't know, maybe it shouldn't be optimal, but in any case, it's sort of a little bit strange, one way or the other. Another question is, the greedy algorithm always gives the best underapproximation for the number 1. Is this true is 1 the outlier? Are there any other numbers for which the greedy under approximation always is the unique best one? And in any case, is it possible to somehow describe all the numbers for which the n-term greedy under approximation is best, and also to describe all the numbers for which the n-term greedy under approximation is not the best, right? Where you can give like examples why it's not the best. So that is the question I wanted to investigate and have some answers, in fact. So I'm going to state some results, probably not with any proofs, but the proofs are all on the paper on archive. So remember Sylvester's sequence. S sub I, where every SI is product, say SI plus 1, product J goes from 1 to I, S sub J plus 1. And what Sylvester showed, in fact, was if you take the sum of the...
It's a little hard to see, maybe a little bigger from now on.
I think it's the focus. We once had that problem before.
Could be.
Yeah.
I pinned Mel, and it's big enough now so I can read it, but it looks blurry.
Yeah,
So
so
Mel
I am constrained with the equipment in front of me, which is a this document camera type thing, and anything beyond that is
Can you move it closer?
well, I move it closer and you see less, but
Well,
is that better?
It's much clear. It's much clearer that, yes, to me it is.
Oh, all right. So maybe I'll try and do it like this, but it means less on the screen at any time. So remember Sylvester. SI, I goes from 1 to infinity. S1 is 2, and SI plus 1 is product Sj, J goes from 1 to I plus 1. And this has the following property. If you take the sum of the first n terms of this sequence, of course, this is strictly less than 1. But in fact, there's a prettier identity which says that, which is what in fact gives rise to the sequence, 1 minus the sum and greater than 0. 1 minus the sum of these first n Egyptian fractions is in fact equal to 1 over the product of S sub I goes from 1 up to n. And this is exactly the identity. This is true for all n. And this is exactly the identity that says that the n plus first term is the product of the previous terms plus 1. Okay. And one might ask, are there other numbers for which we can make a very explicit statement about what comes out of the greedy algorithm? So there's the following theorem. I have to say that the literature on Egyptian fractions is semi-infinite, and I know a set of measure 0 of it. So to my limited knowledge, what I'm about to say is new, but it's hard to believe that it is. So there's the following result. Suppose I take a fraction P over Q between 0 and 1, where P and Q are positive integers, such that P divides Q plus 1. So for example, theta equal 1 over 1 satisfies the condition then if you apply the greedy underapproximation algorithm, the infinite greedy underapproximation sequence for P over Q is defined by A sub 1 is equal to, let's see, P divides Q plus 1. So Q plus 1 over P is an integer. And and the K plus first term is Q times the product of the first K terms plus 1. So this is exactly Sylvester's sequence in the case P equal Q equal 1, but it gives you some larger class of fractions. All right. So this is useful to know.
So for example, it would work with 2/3.
Excuse me?
It would work with 2/3, for example.
Correct. Yeah. If you take P over Q to be 2/3, then A1 is 2, and AK plus 1 is 3 times the product of all the previous terms plus 1. Yeah. And it's going to turn out that for all the numbers in this class, this greedy approximation, underapproximation, is always the unique best one. But that actually is a little bit difficult to prove. Let me just define or introduce the right terminology for what I want to discuss. So these are really sort of housekeeping results, but this is just a little theorem. It says that if you have a sequence of integers where A1 is at least 2 and AI plus 1 is always at least AI squared minus AI plus 1, then if I take the first n terms, I goes from 1 up to n, this is the n term greedy underapproximation for theta, if and only if, or precisely for all theta in the interval, theta is this sort of half open interval, summation 1 over AI, I goes from 1 up to n, less than or equal to summation 1 over AI, I goes from 1 to n minus 1, plus 1 over a sub n minus 1. So
Do you want 1 over an minus 1, or do you want 1 over an? Because then it'll be there twice.
no, this is 1 over an, 1 over an minus 1.
Oh, okay. Thank you.
And the useful, later on, I'm going to just look at two-term underapproximations. So the corollary of this, which is just the n equal 2 case, is that if you have, so the theta be in the interval from 0 to 1, and you have two numbers, A1 and A2, A1 at least 2, and less than or equal to A2. So so this pair A1 is the two-term greedy under approximation of theta, if and only if, first of all, A2 has to satisfy, this is the
Move it
standard
up,
inequality
up a
we always
page.
find. Oops, yeah. And 1 over A1 plus 1 over A2 less than theta less than or equal to 1 over A1 plus 1 over A2 minus 1. So if you take two terms, two integers, A1 and A2, and A2 is sufficiently big, then the pair A1, A2 is the greedy under approximation algorithm for everything in this interval. And in a bit, I want to understand when the greedy under approximation is not best, even when you're just looking at two terms. Let me just be very precise about what I mean when I say best. So suppose we let En be the set of all n-term sequences of integers that are, the smallest term is at least 1, and they're increasing. Not strictly increasing, but just increasing. So this is my set of n-term sequences of integers, and let theta be between 0 and 1. So u sub n of theta, this is going to be the set of all these sequences, n-term sequences, such that the sum of the reciprocals, the sum of the Egyptian fractions, is less than theta. So I'm looking at all Egyptian fraction n-term under approximations of theta, and little u sub n of theta is the soup of what's in this set. Summation 1 over x sub I goes from 1 up to n, where x sub I is a sequence in u sub n of theta. So every one of these numbers is strictly less than theta. So the soup is less than or equal to theta. And you could conceive of a situation where there are numbers in this set that get closer and closer to the supremum, but never hit it. And the theorem says that never happens. So the theorem says, oh, and so we call u sub n of theta is called the best n-term Egyptian under approximation to theta.
Excuse me, Mel, is it defined though? The soup may not be a rational number.
Well, I didn't say anything about rational. So this is a set of rational numbers bounded above, so it has a supremum.
And it's the best under approximation. Under approximation implies you're adding up reciprocals of integers.
Right. So oh, sure. So I'm defining this term.
Oh, okay.
I could have said pretty good or super wonderful, but it's just the supremum. But the theorem says, what?
Initially, you don't know that there's any sequence that realizes it, and you don't know that there's only one sequence that realizes it.
Correct.
Yeah.
And the theorem says that there exists a sequence B sub I stands for best, 1 up to n, in un of theta, such that this best approximation is in fact this fraction.
Move up.
Okay. So in particular, the best approximation is a rational number and it's strictly less than theta. Right? this doesn't say anything about uniqueness, right? This says that there's at least one sum of n Egyptian fractions, which is the best under approximation to theta. It doesn't say that it's unique. And the reason it doesn't say that it's unique is because it's not unique. Right? There can be multiple ways of expressing this best under approximation, which, among other things, if assuming I just made a true statement, would say that there are many times that the greedy under approximation, even if it's unique, even if it's the best, may not be the best unique under approximation. Okay. So I might be sloppy, but it actually takes me a couple of pages to prove this, and there's a proof written down in the paper on archive. So there are two questions or two statements. So there's the next section in the paper is called when greedy is best. Oops, when greedy is best. And the theorem says, we know that greedy is best for the number 1. For the number 1, the greedy under approximation is Sylvester's sequence, and that is the unique best under approximation for any n-term sequence of Egyptian fractions. And if we let theta be some fraction p over q between 0 and 1, such that the same condition holds, p divides q plus 1, and let ai be the infinite greedy under approximation sequence for p over q. And I already calculated what that is. That is, I get a sequence of numbers that generalizes Sylvester's sequence if we have an increasing sequence of n positive integers such that summation 1 over ai, I goes from 1 to n, is less than or equal to summation I goes from 1 to n, 1 over xi is less than theta, then ai equals xi for all I from 1 up to n. So for this somewhat larger class, well, I only had one fraction before, now I have infinitely many. So for this infinite set of fractions, it's for every n, there is a unique best under approximation, and it's given by the greedy algorithm, right? So that's a bit of new knowledge, I think. And the proof is hard, and it uses essentially, so the original proof of the conjecture about the Sylvester sequence and under approximations of 1 was proved by Curtis and Takanuchi about 100 years ago. And a couple of years ago, Sundararajan put up on archive a beautiful little paper which gave a different proof of that result. And what I use is the method of Sundararajan, which uses essentially Muirhead's inequality. Now, I didn't know Muirhead's inequality because I never studied math when I was in college, certainly didn't study it in high school, so I never took any of these sort of Olympiad type exams. But it turns out that everyone who's studying for the Math Olympiad learns Muirhead's inequality because it solves all sorts of Olympiad type problems, right? It's an Olympiad type problem is prove some strange identity you've never seen before. But it turns out it's always a special case of Muirhead's inequality. So in any case, this gives a class of numbers for which under approximation, best under approximation comes from the greedy algorithm. But we know because I gave, I'm sorry, yes? Is there a question? No, okay. So, but we know that's not always the case because I gave some examples of numbers for which the best under approximation is not the greedy algorithm one. So when greedy algorithm is best, well, it's best for numbers of this form, P over Q, where P divides Q plus 1. And so the next question you want to ask is, when is greedy best? Right? So needless to say, in my paper, I cannot resist using this as the title of one section and this as the title of the immediately succeeding section, right? When greedy is best, when is greedy best? So I had written down a few minutes ago a criterion for how do you know if you have two numbers A1 and A2, A1 less than or equal to A2, so long as A2 is sufficiently large, which means bigger than A1 squared minus A1 plus 1, then 1 over A1 plus 1 over A2 is the two-term greedy under approximation for all theta in this interval. So I just want to look at a couple of examples to show things that can happen. Well, maybe I can do that quickly. So we're considering the case n equal 2. So I can look at A1 equals 2. So A1 squared minus A1 plus 1 is 3. So I want to look at numbers A1 and A2, where A1 is 2 and A2 is at least 3. Let's see, what's an example of number at least 3? Well, 30. So if I take a half plus a 30th, which I think is 8 over 15, this is less than a half plus 1 over 29, which is what, 31 over 58. And for any number theta, in this interval, this is the two-term greedy under approximation. And in fact, you can't do any better than this, but you can equal that because a half plus 1 over 30 is equal to a third plus a fifth. So this is a best two-term under approximation to every theta in this interval. But a third plus a fifth is equal to this. So you have a second two-term under approximation. The under approximation isn't unique. Okay. Let's look at one other example. Suppose I take A1 equal to 3. So A1 squared minus A1 plus 1 is 7. So I want an A2, which is at least 7. So maybe I take 1/3 plus 1 over 17, which obviously is less than 1/3 plus 1 over 16, which is 19 over 48. And 17 is bigger than 7. So this says that 1/3 plus the 17th, this is going to be the best. Sorry, this is going to be the greedy. This is the greedy under approximation. If you take any number theta bigger than this number, what is this number? This is 20 over 51. If you take any number theta, which is bigger than 20 over 51 and less than or equal to 19 over 48, the Egyptian under approximation that you get from the greedy algorithm is 1/3 plus a 17th. But unfortunately, 1/3 plus a 17th is less than 1/4 plus a 7th, which is 11 over 28. So in this smaller interval, from 11 over 28 to 19 over 48, the greedy algorithm gives you 1/3 plus a 17th, but 1/4 plus a 7th is a bigger and better under approximation to theta. All right. Okay. Now, I actually have a kind of program that's written down in the paper, which allows one to calculate all the times the greedy algorithm of 2 terms is the best, and all the terms it's not the best under approximation. So if you take the interval from 0 to 1, you can write this as, we have these, what I call these harmonic intervals. So a harmonic interval is an interval of the form 1 over A1 to 1 over A sub 1 minus 1. All right, for A1 equal to or greater than 2. And this is, I'll call this I of A1. So from 0 to 1, this is the union of all of these intervals. And if I take a harmonic interval, in this interval, the greedy algorithm, the first number it gives you is 1 over A1. Right? Because 1 over A1 is smaller than everything in here. And I can actually compute for each of these intervals what numbers give you the best, for what numbers the greedy algorithm gives you the best Egyptian fraction under approximation, and for which it doesn't. So just as an example of what the method produces, we can state the following. So I want to consider the interval I of 2, which is the interval from 1/2 to 1. And this interval is a union of what I might call harmonic subintervals, 1/2 plus 1 over A2, 1/2 plus 1 over A sub 2 minus 1, where A sub 2 goes from 3 to infinity. So this interval is this countable disjoint union of these subintervals. And the 2-term greedy under approximation for theta between 1/2 and 1 is the unique best under approximation for all theta in this interval from 1/2 to 1, unless it's in one of the following 3 subintervals. Let me call this, I don't have to keep writing. This is J of A2. Or J of, yeah, call this J of A2. For all theta except in J of 6, J of 12, and J of 30. So this interval decomposes into these infinitely many pairwise disjoint intervals. In all but these 3, the greedy under approximation is best. In these 3, it's best and unique. In these 3, it is best but not unique. All right. So in some
Did you
sense,
prove-
that tells you.
Did you prove that?
Yeah. Yeah. Yeah, no, there's a proof. It's easy. I mean, yeah, I prove it. Let me just write down one other. Suppose we look at I3. So that's the interval from 1/3 to 1/2. And again, this decomposes into intervals of the form 1/3 plus 1 over A2, 1/3 plus 1 over A sub 2 minus 1, where A2 goes from 7 to infinity. And so the greedy
Yes,
algorithm,
correct me if I'm wrong. If you try taking numbers less than 7, then you end up oozing into the I2 regime, right?
yeah, if you're hitting a number less than 7, you don't have the greedy algorithm. The greedy algorithm gives you numbers 1/3 and A2 greater than or equal to 7. So yeah, so you're not in this interval at all. So the greedy algorithm is best for all theta except in the intervals 9 over 20 and 11 over 24, and sorry, is best and unique. And the interval from 11 over 28 to 19 over 48. All right. Sorry. Yeah, the greedy algorithm is best except in these 2 subintervals. And in other intervals, there are a finite number of intervals in which it is not best, and everywhere else, sorry, there are a finite number of intervals in which it is best but not uniquely best, and a finite number of this infinite set of intervals in which it is not even best, and that's everything, right? So that's a complete classification of what happens in this interval from 1/3 to 1/2. Right? And again, the numbers are all written down in the paper, and it's easy to check. I just want to add 1 or 2. I just want to mention some open problems that are connected with this, because it's the problems that are. It's what you can't do that's the interesting thing. So the simplest question is, for what rational numbers P over Q in 0, 1 is the infinite greedy algorithm, greedy under approximation sequence best for all n. So I proved it for a certain set of rationals. We know it's not true for other rationals, but when is it true? And there's no reason just to look at rationals. You can also ask the same question about irrationals. Okay? Is there something we can say about that?
What do you think an answer would be here? I mean, it's clearly true for some and false for some. You know, what's better than a tautological answer?
Well, for
What-
example,
what sort of-
here, it's all rationals where P divides Q plus 1.
And so that's a subset, and it's sufficient but not necessary. Yes.
Correct.
So you want a necessary and sufficient condition that
No.
might be stated in some.
Well, that would be great, but what about a different set of rationals? Still not necessary and sufficient, but other ones.
More inclusive for sufficient conditions. Yeah.
Yeah,
Okay.
or a completely unrelated description, but yes. Also, I can completely analyze the case of two-term Egyptian fraction sums, but for n greater than or equal to 3, that's much harder, I think. And I'll just mention one last problem. So in the famous Erdős-Graham sort of survey called something like Problems and Results in Combinatorial Number Theory, or Solved and Unsolved Problems in Combinatorial Number Theory, they say the following: let theta be some number between 0 and 1. So un of theta is always the best n-term under approximation. So they state the following without a proof or a reference. It is, for all theta, there exists some number n naught such that u sub n of theta can always be obtained in the following way. So this is for all n greater than or equal to n naught plus 1. You take the best n naught term under approximation, no matter how you get it, and then you add the best n minus n naught under approximation for theta minus u sub n naught of theta. So even this isn't obviously true, but they say this is true, and this is always obtained by the greedy algorithm. So this means for every theta, if you start to calculate if you want to calculate the best n term under approximation, from some point on is always given by the greedy algorithm. We know that it's not always given by the greedy algorithm from the beginning because we have counterexamples. But the assertion is that from some point on, this is true. So they say, what?
What about algorithmic aspects? I mean, in order to find un of theta, we know it's always realized by some sequence. What's
Right.
the search? What's the search size? I mean, how many sequences do you really need to check through? There's some finite list. You can bound the size, but I think it comes out a very poor bound unless you're clever.
Yeah, so the proof is in some sense algorithmic, in the sense that you do, a certain number of things a finite number of times. You do a finite number of things a finite number of times, and you get the answer. You are probably right that if you do it in the sort of simple-minded way that my proof goes, you get some very big number. But I don't know anything beyond that.
Okay.
what they actually say is not only this, but they claim this is true for rationals, but it is not difficult to construct irrationals for which this is not true. In a few years, I will be, I hope, with them in the Olam Haba, and I can ask them directly what they had in mind. But at the moment, they are inaccessible to me. Anyway, that is the short story and the long story. So, yeah. So that's what I needed to prove. That's the story. So, you know, there is this vast subject of Egyptian fractions, and people do a lot of things with them. And
Are there practical applications for them?
well, my normal answer is who cares? I was once long ago, really long ago, I was visiting at the Weizmann Institute. And at that time they had a department of applied mathematics, and that was it. And I was talking to someone on the faculty, and I said, you know, why do you call what you're doing applied mathematics? And he says, if I can make a living from it, it's applied. So
Ernest called number theory applied mathematics because it's the only branch of mathematics to which all other branches apply.
well, you could say the same thing about geometry and analysis, and you know, but I have never been overly excited about, I mean, there's a lot of applied mathematics, which is really great mathematics. And it's great mathematics, in my view, for me, not because it's applied, it's just beautiful mathematics. So, you know, if you're trying to understand, you know, fluid flow or particles of one sort or another moving around, I mean, there are all sorts of fantastically interesting mathematical problems in so-called applied mathematics, but I don't care about applications. In fact, I sort of have a disagreement with the American Math Society about this, because every year they trot out a few people to go to talk to the Congress and Senate science committees about mathematics, and they only give applications of mathematics. Last year, in addition to that, they also trotted out the French Fields medalist, who was a politician. All right, he's in the French Parliament, and he failed to be elected mayor of Paris. And I have no doubt in a couple of years they will send this ex-football player, who's now a mathematician, to Congress to show them that a mathematician can be a real man. But and I don't object to showing the Congress people applications of mathematics. I only object to it being the only thing they talk about and nothing about the aesthetic part of mathematics. So,
well, the way I've heard some people approach it is they show them mathematics that was non-applied for a very long time, like primes, and all of a sudden became applied. And they use that to justify grants on the grounds that you never know what people will need.
yeah, no, I understand the logic, but I would be happy if every now and then they just showed something which is just interesting without
the reason I
application.
ask is sometimes the applications naturally suggest theorems, which would not be obvious otherwise.
Yeah, that's fine. No, it's all good.
It would be better for us if we could get funded like the NIH and not like the NEA.
Well, we're in between, of course. Of course, you can also say why do we need the funding? Right? I mean, most people don't have it and it doesn't.
You need to eat something.
Well, no, not, I mean, the NSF funding. Like one year, I was someone twisted my arm and I applied for an NSF grant for the Cannes conference and for travel. And everyone was used to coming on their own dime. And I actually had to do something which was considered un-American or unethical or something. I gave back half the money. I couldn't spend it. No one needed it. No one wanted it. I was asking people, even like someone came from Russia. You figure from Russia, they could use like $1,000. Oh, no. My university in Moscow is paying for me. I don't need any money. So just couldn't get rid of it. And in the end, I just, I mean, it might have cost the NSF more money to deal with me than if I had spent all the money. They had to figure out how to like reprogram money that was unspent that was coming back from the research foundation of CUNY. But, that was it. So anyway, that's the whole story. By the way, if anyone has 2 minutes, I was sent a 2-minute video. Where is it? Oh.
Is this politics or something interesting?
Oh, it is definitely not politics. The question is, let's see, share screen. This is what I want to share it with. Play.
Excuse me, gonna need to see your proof of vaccination. Oh, now we got the new mandate going on. Right, sorry. I have the app. Oh, Moderna, huh? Heard that one knocks you on your ass. I got the Pfizer. Oh, you're a Pfizer guy. I hear Moderna's better, but not gonna judge. You're normal. Have a good one. Have a good one. Vaccine passport? Yeah, but I need proof of at least 10 booster shots. Where's the AIDS vaccine passport? I'm gonna use an allergy test. Lyme disease, chickenpox, H1N1, rabies tag, H1N2, polio papers. Seriously? Nah, I'm just kidding about that one. Oh. But I will need to see a syphilis passport. Oh, of course. H1N3, H1N4. All right, proof of the herpes vaccine. And what about the herpes booster? I literally got it like 10 minutes ago. Let's see it. All right, and foot and mouth disease, H1N5, H1N6, prostate exam, whooping cough. I'm gonna need your Netflix password. HPV. I actually have HPV. I need proof to show solidarity to the HPV community. I'm gonna need to see your blockbuster card. Tetanus. Negative test for the black plague. Tetanus booster. I don't have it. I'll give it to you now. Proof of political party, proof of diversity. Are you serious? We already have 2 white guys in there, okay? That's our limit. Okay, I'm Jewish. What do you think this is, 2021? You're gonna have to be way more impressed than that to get in here. You got like a 23andMe test results? Yes. 50% Ashkenazi Jew, 0.000027 Native American. Why didn't you just tell me that? Got an anti-racist card? All right, now I just got to check your white guilt score. 9.7. Wow, not bad, man. All right, put your mask on and show them your receipt. I actually lost the receipt, so how are we supposed to give you your laundry if you don't have the receipt? Get the fuck out of here.
So someone sent me an email today saying that he was busy, he couldn't come to the seminar, but he was sending me this instead. So.
Well, at Towson, they're requiring students get vaccinated, and I asked them why they left out faculty, and they said the TU Health Center is not allowed to administer vaccines to faculty because their legal authority is only over students. So when when the president of Towson wanted us vaccinated, they had to hire an outside contractor to come down and give us the boosters because the health center wasn't allowed to.
Well, at CUNY, faculty, staff, students are all required to be vaccinated. And if you refuse to be vaccinated, they drop you from the rolls.
They don't drop you here. They just require that you test every day. You have to go down for a test at the health center every day.
I think at CUNY, you have to be vaccinated.
I think students only have to be vaccinated if they have a class that meets on campus.
Oh, yeah, sure. Yeah.
Sure.
No, off campus, it doesn't matter. But you can't be on campus without proof of vaccination.
Yeah.
They're supposed to actually take mine away because they also have random drug testing. And my name came up in the random thing.
Mine
And I
too.
said, I'm not going to drive to New York to be, you have to be tested at CUNY. You can't just like go to, your neighborhood, whatever. Doesn't matter because I don't plan to be on campus this semester anyway, but still.
That'll be waiting for you in September 2024 when you go back to campus.
Right. Could be. Or, by that time, it might be like the video. You need, a whole list of 20 things that have been done to you.
Just in time for COVID-24.
Yeah.
There was this course that faculty at CUNY had to take on, I forgot exactly, that you had to learn about how to defend yourself or how to, I guess, be sensitive to other people. And you are forced to take it. If you don't take it, then at one point or another, they'll stop your salary. And so I retired in 2017, but they kept on sending this every semester. Will soon quit if you don't take the course. And it was clear that, one hand was not talking to the other hand. And they kept on saying it. I don't know exactly when they discovered that they were just talking to someone that